Hello, welcome to Math 6550. This is Classical Mathematical Finance. I'm Alan Anderson. I'm your teacher. And this is a very interesting class. It's a little different than what you're used to. It's a very applied math course. In fact, this is one of those fields where it actually overlaps heavily with not just finance and math, but also computer science and even physics. A lot of the math that we'll be using here was originally taken from physics. So it's very much an applied course. We're not going to spend any time doing any actual proofs like in your regular math courses. Instead, we'll be writing computer code for developing the models that we'll be using throughout the course. Now, we're going to use a very basic, simple programming language called VBA, which is Visual Basic for Applications. And if you've never seen it, it's actually in your copy of Excel. And it's designed to be very English-like. The statements are designed to be very much like English statements. It's been around for a very long time, so it is certainly not the most powerful language out there, but it's one of the easier ones to learn. And even though it's a very old language, dating back to the 70s, it's still heavily used on Wall Street because as being part of Excel, it's easy to develop models and other important results in an Excel spreadsheet. And then in order to increase the speed of the code that's been written, then the computer programmers can turn it into something more powerful like Python or C++, whatever the case may be. But for simply developing ideas, developing new models, for example, or developing hedging strategies or something along those lines, Excel combined with VBA is still a very powerful and heavily used tool, not just on Wall Street, but I mean everywhere. But as far as the material we're looking at, that is where you primarily see the stuff being used. So what we're going to do here is first start with the very beginning, the basics that are absolutely fundamental to all of finance, by which I mean the time value of money. Okay, now everything in finance ultimately comes down to the time value of money. So while in the beginning we won't be looking at derivatives as such, which will come later on, we'll be looking at the fundamental notions of finance that on which everything else rests. And by the way, I just want to mention that the syllabus has been posted. If you want to take a quick look at it, you'll see, let me just go get mine open, all the details that we need for this class. For example, my information, how to get a hold of me, the name of the course, the fact that it's the summer of 2024. Asynchronous online means that the courses do not meet, of course, in person, but there's no set schedule for the courses either. In other words, I've had online classes where we met at a specific hour every week. That's not the case here. The whole point of this course is that you can follow along at your own pace. And so what that means is what you'll need to do is watch the lectures when you get a chance, and then there'll be assignments scattered throughout the course in VBA. And so it's a very flexible setup. And it runs for the next 6 weeks, so it's not too terribly accelerated. We'll be going roughly twice as fast as we would during a normal semester. And then again, we'll give you plenty of time to keep up with the work. And also, I just want to mention here that since we don't have an actual classroom, there's also not a place to have office hours. So instead, what you can do is if you want to meet, you can call me or send me an email, and then we can arrange a time when we're both available, and we can have a Zoom session like the one we're in now, and then we can go over whatever you want to go over. Okay, so in other words, if you feel the need, you can get in touch with me and we'll have a session. Also, I want to mention that, of course, these sessions are being recorded. What I'm going to do is post them on Blackboard when they're ready, and I'll let you know when new ones are there, so you can watch them when you get a chance. And also, so are the notes, as you'll see in a second. All of my notes were written in PowerPoint. And now here's something I do want to mention, though, as far as that goes. These slides are full of equations and sometimes graphs. Now, all of these were written on a PC. So you're probably wondering, why does that have anything to do with anything? It's been my experience that if you open up these slides on a Mac, sometimes the equations do not look right. They get mangled, they get distorted. The graphs, they can get distorted as well. So what I've done is I've posted both a PowerPoint version of these slides as well as a PDF version, so that if one of them doesn't look right in your computer, the PDF will always look right. That's something I do know, that the PDF is simply a picture of the notes, and so therefore it can't be distorted. Unlike, unfortunately, the equation editor that I use for this PC is very powerful. It's called MathType, in fact, and it is very heavily used by professional type people. I mean, journals and that type of thing. But unfortunately, it's not compatible with the Mac, or not necessarily. So it can be a problem. So that's why you'll see both PDF and PPTX, if you were wondering about that. But as far as the syllabus is concerned, um, there's a lot of discussion here about what topics we'll be covering. And it looks really terrifying, but it's really not. It's a very, very important and interesting area of study. And in fact, if you find it to be extremely interesting, there actually are graduate programs out there which focus exclusively on this type of material. So it's there if you want it. So there is a book that I've written the notes based on. It's called Implementing Derivatives Models. And its companion, I guess, is this classic textbook called Futures, Options, and Other Derivatives by John Hull. It's been around forever. It's the gold standard of derivatives textbooks. And they're up to, I believe, the 11th edition now. So basically, what Clelau and Strickland have done is they've taken Hull's book and they've used his notation and his models to create algorithms to help us implement Hull's models. Okay, so if you read the two books side by side, you'll see they're very similar, except that Clelau and Strickland are adding all the computational details. Hull, for some reason, never got around to doing that. He's really a finance guy, not a computer guy, and so the book, if you read Hull, you will not find any hints as to how to write code, but you'll find everything else you need. It's really a spectacularly important book. If you really mean to work in this field, you really should have a copy of Hull's book, but it's not necessary for this class. But my notes are largely based on his book. Not all of it. I mean, the discussion about time value of money is all mine, but the rest of it, I try to follow along what he's doing, including his notation. So anyway, what are we doing in this class? Well, let's see. We have the time value of money, which we'll be looking at today, yield to maturity. Now, these first four topics, all are involved with interest rates, the measurement of risk, interest rates, the management of interest rate risk, that type of thing. And then we can move on into our study of derivatives, which begins with forwards and futures. And then we move into the most complex topic of them all, which is options and option pricing theory. So the rest of the course will involve understanding what options are and how they're used in the marketplace, and also how to price them. Now, all of this material has a very interesting history. The derivatives themselves, in particular, options, have been around for a long time, but what really held up their acceptance in the financial markets was the fact that they were so complicated that it was very difficult for anyone to understand how they should be priced. Okay, so it took until 1973 before the first proper option pricing model came along, this Black-Scholes model, which you'll see here. And once the model came out and people could see how straightforward it was, suddenly trading in options just went through the roof, because they're so powerful and they're so useful that once it was understood how to price them properly, the trading volume just exploded. And so now we see all kinds of options out there in the marketplace, which we will discuss as we go along. And what we want to focus on is the correct way to price them and understand the logic behind how they're priced in the marketplace. We also want to consider some risk management features, such as these Greeks, as they're called, which help us understand how much impact they have on our existing investments. If you, for example, have a portfolio of stocks and you buy options for that portfolio, you need to understand how that's going to affect the risk that's involved with your portfolio. And then now this last topic here, the binomial option pricing model, is a very sophisticated extension of the Black-Scholes methodology to price more different kinds of options. And so when all of this is done, you'll have a very good background in financial mathematics, in particular, the pricing of derivative securities, and you'll also have some more programming skills. So we're going to do a lot in the next 6 weeks. All right. So anyway, why don't we get started with the time value of money? Now, what I'm going to do with this is I'm going to show you how this works in Excel, although you could certainly do everything we're about to do with a calculator if you chose to. But I think it's a good idea to get into the habit of using Excel because, of course, eventually we'll start using VBA. And so if you're not really a big Excel user, we want to get comfortable with it. All right, anyway, so what exactly is going on with the time value of money? Well, as I mentioned before, it really is maybe the most fundamental concept in all of finance. And really all it refers to is the idea that receiving a sum of money in the future is less valuable than receiving the same sum today. Of course, if somebody offered you, let's say that you did some work for somebody and they owe you $1,000, when would you rather collect it, now or next year? I mean, really. Now, everyone immediately understands that it's better to have the money now, but if you ask them why, they may not be able to come up with a good explanation. Certainly, it's going to be easier to spend it if you have it now, but what really separates the receiving of a sum now and a year in the future is that if you receive the money now, you can invest it and earn interest, okay, for a year, which would not be possible if you have to wait a year to collect that same sum. So in other words, it's that interest rate that's really driving the value of the sum today versus next year. So we're going to define 4 basic concepts: the future value of a sum, the present value of a sum, and then we're going to introduce another type of cash flow, which is called an annuity, and we're going to calculate its future value and its present value. Once we have these done, there's more, but this is the most important set of concepts that we'll need. All right, so we'll start with the future value of a sum. This is something we all think about on a regular basis. If you put money in the bank now, how much will you have in the future? That's really what this is all about. And of course, this is essential for planning. You want to plan for buying a house, for example. You want to plan for saving for a child's college. You want to plan for retirement, for example. All of these require us to understand the time value of money, right? So if I put money in the bank now, down the road, it'll be worth more than it is now. Why? Because the bank is giving me interest. Now, this process that we're following is referred to as compounding. And so what we're going to see now is algebraically how to calculate the future value of a sum. All right, well, first of all, here's the actual equation, the first equation of the course. And what is this actually telling us? All right, well, all the terms are identified in the next slide. I'll tell you what, let me copy these into here so we can keep an eye on them all. All right, well, FV clearly refers to future value. P stands for present value, which is the amount we have now. Okay, this is how much we deposit in the bank today. R is the annual rate of interest. Now, by the way, I just want to mention with any type of formula like this, the interest rates are always expressed as a decimal. We don't use percentages, we use decimals. So for example, 8% would be listed as 0.08. And then N is the time horizon. Typically that would be years, but it doesn't have to be. Also R, it's not absolutely necessary that the interest rate has to be expressed as on an annual basis, although it usually is. That's not always the case. So basically what we're doing is we're taking the present value and multiplying it by 1 plus R to the nth power to come up with a future value. For example, we start with a sum of $1,000 today. We invest it for 4 years at a rate of 3%. What is the future value of the sum? All right, so let's use the notation from the slides. PV or P. Yeah, some books use P, some use PV. I think Hull uses P, but I'll put P here just to be on the safe side. But if I ever type PV, you know what I mean. Okay. All right. 4 years. So N is 4. And again, it's understood here that we're talking about years. R, the rate of interest, is given to us as 3%. So we're going to be calculating F for future value. Now, we can do this one of two ways. We can use the algebraic formula, which again, I'll copy here so we can refer to it. Oops. Yeah, we just have to adjust that a little bit. All right, that'll do. There we go. That should do it. All right, so let's do that first. So you'll have P times 1 plus the interest rate. And in Excel, by the way, the way you take an exponent is this key. This symbol is called caret, C-A-R-E-T. It's found by hitting Shift 6, and then you hit or you choose N as 4. And let's round that to 2 places because it is, after all, dollars and cents. And what you're seeing here is that if I put $1,000 in the bank right now for 4 years, and the bank pays me 3% per year, when the 4 years are up, my balance will be $1,125.51. That is the future value of the original $1,000. And in addition to that, we can determine that the interest that we earned, although the slide doesn't ask for this, the interest is nothing but the future value minus the original present value. And so our interest is $125.51. Okay. That's it. And that's all there is to it. So future value is a very straightforward idea. Now, of course, if you notice, we're assuming that during this time period, nothing changes. Now, you may be aware that banks offer a product called a CD, or certificate of deposit, where you put your money in the special account and you lock in a specific rate of interest in exchange for keeping your money there for a fixed length of time. So if we put our money in a 4-year CD that pays 3%, then our assumptions will definitely be met. Okay. Anyway, by the way, this interest can be decomposed in a very interesting way. Let me just briefly run through this with you. All interest falls into one of 2 categories. We have simple interest, which is interest on the original principal, and we have compound interest, which is interest on interest. Now, how does that work? Okay, well, think about this. At the end of the first, actually, let me draw a little diagram here to help you see what this is all about. This is a timeline, as it's called. Actually, let me just. All right, sometimes it works, sometimes it doesn't. You never really depend on technology, but we'll do as best as we can. Let's try that again. This is today. Okay, so we put $1,000 in the bank. Now, we often illustrate that with a negative sign to indicate that this is money coming out of our pockets. Now, in 1 year, how much will we have in this account? We earn 3% worth of interest. Okay. I'm telling you, sometimes this works, and like I said, and sometimes it doesn't. So we earned $30 worth of interest during the first year. That $30 is entirely based on the original investment of $1,000. So we earned $30 worth of interest, all of which is what we will call simple interest. Let's see, maybe I'll handwrite this. I'm trying to line it up properly. Fine. Now, in year two, this is where it gets interesting. The 3% is now being based on not $1,000, but $1,030. Okay, that's the key to the whole thing. Oh, let me get out a calculator real fast. So the new balance is $1,060.90. So their total increase in our balance is $30.90. So the total interest, by the way, let me add this over here. Simple and the total are each 30, but here all of a sudden the total interest is also is sorry, $30.90. So the simple interest never changes. It's 3% of the original principal. So the simple interest is 30. So where do the other 90 cents come from? That's what we mean by compound interest. That's our 90 cents. And the reason why we're getting that is because if you notice, this 3% is being applied to the original principal of 1,000 plus the $30 worth of interest from the year before. So that's where that extra 90 cents is coming from, 3% of $30. That's what we mean by compound interest, interest on interest. Okay. And then if you go ahead to year three, balance is now approximately 1092.73. So our total interest this year, so remember our balance went from 1060.90 up to 1092.73. So that's 31.83. And since the simple interest is still $30, that implies that the compound interest is $1.83. Uh-huh. So you can see what's happening now. The simple interest is exactly $30 a year. That'll never change. It's the compound interest that will grow because it's being based on a larger and larger balance. And then finally, at the end of the fourth year, we're going to have as we predicted, 11, 25, 52, 51 rather. Now, sometimes by doing it step by step like this, what did I do? Sorry. Yeah, for some reason, there we go. Sometimes you can run into slight rounding discrepancies when you break it down like this, but we did end up with the same result. And now, once again, you can see the total interest is the difference between the two ending balances, 1125, 51 minus 1092.73, 3278. And so the simple is 30, as it always will be. Now the compound interest, 278. And so what you can do now is say, well, listen, in this case, the simple interest would just simply be 4 times 30. The compound interest, you could do this in one of two ways. You could add up the individual compound interest. We have 0 plus 90 cents plus 183 plus finally 278. And then when we add them up, oh, what do you know? They're the same as we predicted. Total interest 125.51. So now we not only have the total interest, but we have a breakdown between the simple and the compound interest. Huh. Now, what's interesting about simple and compound interest is the way they grow over time. So what I'm going to do is show you a couple of quick graphs. The simple interest grows at a linear rate. It's just a straight line. In this case, the slope is 30. In other words, every year that goes by, we earn another $30 worth of simple interest. Compound interest starts out very slowly, and then now that's interesting. You see how it grows very slowly at first, but eventually it'll grow so rapidly that somewhere along the way, we'll actually be earning more compound interest than simple interest. Now, this might take 20 years, but it will happen eventually. In fact, this is the secret to early retirement. Starting your savings young. In other words, the difference between saving for 30 versus 40 years can mean almost doubling the interest that you've earned. It's really amazing how it piles up over time. Okay, so that's future value of a sum. We just saved this real fast. By the way, I'm going to post this on Blackboard along with the any notes that I write on these slides. And the slides themselves are already posted. Okay, now the reverse of future value is called present value. And what do we mean by a reverse? Instead of asking the question, if I start with $1,000 now, how much will I have in the future? What if I need to save? Let's say my goal is to have enough money to make a down payment on a house in 5 years. Let's say I've found out that I need $20,000 to put a down payment on the house that I want, but I need it in 5 years. How much do I have to put in the bank now to make sure that happens? That's equivalent to saying, what is the present value of $20,000 received in 5 years? Okay, so what we're doing here is the opposite of compounding. This is called discounting. And as it turns out, all we're going to do is algebraically rearrange that same formula to solve for PV. In fact, you can see that's exactly what's happened here. Let me just go get the other one back. Let's see where, okay. So basically, algebraically, all we did here was divide both sides by 1 plus r, okay, to the n, I mean, and to get to this point. Okay, and of course, this can also be rewritten if you prefer. So it's more obvious that they're simply the inverses of each other. Okay, so let's look at a quick example. How much do we have to put in a bank that pays a rate of 5% in order to be worth $1,000 in 3 years? All right, let's do that. I'm going to move this to the second tab. And this time, I'm solving for P. So I want to have $1,000 available to me in 3 years. This time it's 5%, 3 years. and then I'm solving for P. So algebraically, let me remind us how this works. Oh God, look at that. There we go. So it'll be PV. I'm going to divide. I think it'll be easier that way. Over 1 plus R raised to the third power. And rounding to dollars and cents. That's 863.84. So therefore, if I want to have $1,000 in the bank in 3 years, when the bank pays 5% per year, I have to now deposit 863.84 to make sure that that will be the right amount that I have in my bank account. So this is my future value. Sorry, present value. This is my future value. Now, what this also implies, by the way, is that the total interest I earned along the way would be the difference between the two. Okay. So now in this case, calculating the simple and compound would be more messy, but we could do it if we really needed to. But anyway, the bottom line is by putting our money in the bank for 3 years, we earned under 36.16. So therefore, we have exactly $1,000 in 3 years. Excellent. By the way, you may not realize it, but a lot of financial securities in the marketplace are priced as nothing but the present value of their future cash flows. So in other words, just as a quick example, suppose that a treasury bill has a face value. And by the way, we'll be spending a lot of time talking about interest rates and bonds in the future of this course. The face value is how much you'll receive on the maturity date. In fact, why don't we use the same example? If the rate of interest is 5%, then the treasury bill have a price today of 863.84. In other words, you would go to the treasury. Well, you go out in the treasury market and you would buy this 3-year treasury bill for 863.84, and in 3 years you'd have exactly $1,000. In fact, this is how savings bonds work. In the treasury market, the bills actually don't go out more than a year, but still the principle is that if you did have one that lasted 3 years, this is how it would be priced. So just as an example of this, or savings bonds definitely work this way, and they go out quite a few years into the future. For example, a 20-year savings bond with a face value of $1,000. And when the interest rate is 5%, would have a price of, and then what you would do is the same thing, except that this time it's 20 years. 376.89. So I buy it today for my child's college, let's say, and I pay 376.89, and in 20 years, it'll be worth $1,000. Okay. So this is present value. So you'll see later on that bonds are priced this way. Stocks to a certain degree, there's always present value calculations involved when we price any security in the marketplace because the cash flows take place in the future. Okay. All right. Now, what about compounding frequency? Now, up to this point, we've been making an extremely strong assumption that interest is credited to our account once a year, and that's it. That is not a very realistic assumption. If interest is paid more frequently, then we have to take that into account with our pricing models. Okay. Just as a quick example, when you go to the bank and put your money in your savings account, that interest is actually being credited to your account on a daily basis. In other words, you're getting a tiny, tiny, tiny amount of interest every single day. And so In that case, we say that the interest is being compounded daily. So when that happens, these formulas have to be adjusted. So actually, let me just briefly mention here the types of compounding you may run into in practice. They could be annually, which means once per year. And by the way, this in these slides, the letter M is going to be used to represent what we call the number of compounding periods per year. So M, let's make a little chart here. Annual means once a year. Semi-annual means twice a year. Quarterly, of course, means 4 times a year. Monthly means 12, and daily is 365. Those are the only ones you're likely to run into in practice. Anything else is not likely. It's rare. These are the standard ones. It turns out that this affects the present and future value of the sum. Okay. So the formula, as you can see, has become a little bit more complicated for future value. Okay. In fact, let me go back and get the original one just so you can see them side by side. And you see where the change was made. So what's happening here is that in this first case, R and N are defined in terms of years. Okay, R is an annual rate, N is a number of years. Down here, for example, if M is 4, that means this ratio is a quarterly rate of interest, and this exponent is not the number of years, but the number of months. So in other words, the M adjusts the formula to the frequency with which interest is compounded. Now that, of course, makes things a little messier for us, a lot messier. So, for example, oh, and by the way, of course, here's the corresponding present value formula, which I think I will put on the next slide or the next sheet. But it's the same principle. Okay, you're just adjusting the rate of interest and the number of periods so that it is consistent with the compounding frequency that we're earning or paying, as the case may be. Where was it? There we go. Okay, let's go look at an example of the future value. Okay, here we go. We're going to start with the sum of $1,000. That's our present value. And the annual rate is 4%. And it's a 2-year investment. What's different now, though, is that we're going to calculate the future value, but we need to keep in mind the value of this M term. Okay, so M in the first case will be 1 for annual. All right, we're going to do this 4 times. Here we'll have semi-annual. Oops, wrong one. Then we'll have quarterly and then monthly. And what we want to do is pay close attention to how this affects our results. Okay, it's not just algebra we're looking for here. We want to understand what's happening. Okay, I'll label these as well. So later on, when you're looking at this, you won't say, what is going on here? All right, so then we have quarterly. And then we have monthly compound. All right, now what I would encourage you to do with these formulas, by the way, I realized I goofed this up, is make them general enough so you can move them around and reuse them over and over again. So here's what we're going to do. We're going to use cell references instead of constants. So for example, here I'll have P times 1 plus the ratio of R to M we have to be very careful with the parentheses. And then here we have a ratio of N times M. Um, oh, I know what I did. Hold on one second. I just remembered, some books use the letter T for time. This book is using N. I just remembered I'm being inconsistent here. Sorry about that. No wonder the formula didn't look right. Yes, so N here is being used to represent the actual time, and then M is the compounding frequency. So by setting it up this way, and I'm going to round it, make sure 2 digits are showing. What I can do is just copy across. Oh, wait. That doesn't look right. What did I do? Yeah, I don't think that's right. I don't know why it's not working. Well, obviously I've goofed in some very important way. Let's try that again. I'm going to put 1 plus R over M raised to the N times N power. And then the entire expression will be multiplied by the principal here. Okay, yeah, clearly something was wrong before. Yeah. Okay. Sorry about that. Now, look at what we have. Look at the future value. Went from 1081.60 to 1082.43 to 1082.60, 86 rather, and then 1083.14. Now, if you break it up into simple and compound interest, what you'll notice is that the simple interest doesn't change. The simple interest is completely independent of the compounding frequency. It depends only on time and the interest rate. So in this case, the simple interest is $80 because it's 4% times 1,000 times 2 years. So actually, you know what I'm going to do here first? Let me put total interest. It'll be easier this way, which is, as we saw before, the future value minus the present value. And then if the simple interest is always $80, which it is, what that does is it gives us some important insight into what's happening here. Now, we did the compound interest earlier in a very complex way. This is the simple way. Take the total interest, subtract the simple, and what's left is your compound interest. We did it the other way before because we wanted to illustrate why this is happening. But now that we understand that, it's probably quicker and easier to calculate the compound interest by simply subtracting simple from total. So you can see it keeps going up. In fact, I'm going to put together a little chart for you. So we had 1, 2, 4, 12. And then I have 2, 3, and then finally 4. And so this way you can see the pattern that's emerging. There we go. So if I kept increasing the compounding frequency, let's say to daily, the compound interest will go up even further. So in fact, why don't we do that just because out of curiosity. Oh, you know what I forgot to do? I forgot to label these. All right, let's just do one more, even though the slides didn't ask us to do this. Let's do daily compounding. And so all I have to do is change this to 365 and what happened? Oh, I changed the wrong one, of course. That's more like it. Yeah. All right. So it's 328. All right, so here's what I want you to notice. When we keep increasing the compounding frequency, if you notice the compound interest is going up, but it's going up progressively more slowly. Towards the end, jumping from monthly to daily, it only went up 28 cents. Whereas when we go from just once to twice a year, it went up more than 50%. So if you can imagine um, plotting these out, it'll look something like this. It's increasing at a decreasing rate. And in fact, you can see that it's actually converging towards some kind of a limit. This line that I'm drawing here is actually an asymptote to this function. It's converging, but never quite reaching. And in fact, there's a special case where we allow m to converge to infinity, and we have a special formula for this. Okay, let me show it to you. Oh, okay. It's coming up in the slides. Here it is. It's called continuous compounding. And if you notice, the formula is different. There's our old friend E from calculus. Because if you recall, oh, for God's sake. Actually, let's do it like this. This is the way you're used to seeing it. Okay. So then if you look at this formula, you'll see that, where is it? Here we go. If m goes to infinity, this ratio is going to 0, but this exponent is going to infinity. So the end result is PE to the Rn power. And this case is referred to as continuous compounding. with a finite number of compounding periods. This is known as discrete compounding. Discrete simply means finite. So this is a special case. Now, this is really, really important for a course like this because even though in practice you don't normally see continuous compounding, virtually all derivatives models are based on continuous compounding. It's really, there's reasons for that that we'll get into later on, but this is what you typically see. In fact, in Hull's book, he almost always uses continuous compounding. It has to do with, well, all right, like I said, we'll save it for another day to discuss the reasons why. But so here I'm going to have equals P principal. Actually, I'll tell you what, let me do this here and then copy it. So then this M, I'll just write infinity. So the future value will be P times E, which in Excel is EXP. And then the exponent is R times N. And then the rest falls into place. You can see the compound interest only went up to $3.29. That would be considered the asymptote of this function right here. That's what it's converging to in the limit. That requires infinite compounding frequency. Right. All right. So that's the future value. Now, what happens with the um, present value? Interesting question. So we're going to do something very similar. We're going to take a bunch of examples and work it in reverse. We're going to calculate present values. And we're going to see what happens as the frequency changes. So we'll do the same ones. And we'll at the end look at the limiting case. Okay, now I think in the slides there's a different, there it is. Oh, it was here all this time. X just goes to infinity. This comes from, you remember this from Calc 1 or 2. It's towards the very end of Calc 1 or the beginning of Calc 2. Okay. All right. I guess I could have just copied that, but it's fine. Yeah, E is, yes, the limit is X goes to infinity, 1 plus 1 over X to the X. But if you put an R here instead of 1, R is just some constant, then that means E is raised to that power. Okay, I just want to mention that. Now, let's get to the present value cases. We're going to have this time $1,000. Oh, we have to be careful here because this time we're solving for E. The formulas will, of course, be different. So here, the future value is 1,000. The interest rate is 6. It's 4 years. And the present value will be future value divided by 1 plus the rate of interest. Oh, actually, no. I'm using this formula now. So just to be on the safe side, I'm going to do what I did before. I'll do the tricky part first, just to make sure I don't run into trouble with the parentheses. The exponent is the ratio of R over M, negative N over M, N times N rather. And this whole expression is now multiplied by the future value. And so I'll have here B 22 times. There we go. Now, like I said, for these, we don't necessarily have to calculate the interest total and all that. But what we are going to notice is something interesting. Um, Actually, yeah, I'll tell you what, we looked at the interest here. If you plotted the future value, you would see that the shape is very similar. Here we're going to plot the present value. And we're going to just do this different ways. We'll start with semi-annual. So all I have to do is change this to 2. Then we'll have quarterly, monthly, and yearly, and then we'll do continuous. Oops, no, not quarterly compound. M is 4. And then we'll have monthly. M is 12. And then daily. And then we'll do continuous. And now, of course, this one requires a different formula. I'll show you again. Oh, by the way, there's a quick derivation here if you want to take a look at it in a second. Um, Here it is. Okay, so we're going to now gather them up like we did here, except this time we'll just be looking at the present values. And because I've set it up so cleverly, you notice I didn't have to change anything. And so if you were to plot these, what you would notice is that it's decreasing at a progressively decreasing rate. Okay, and this is your asymptote. That's as low as it can go. All right. Wow. Okay. So let's see. So there's a derivation. This is basically the logic behind why those contingently compounded formulas work. This won't take but a minute. And then we're going to look at annuities, where what's happening with an annuity is that instead of getting a lump sum of money paid or received at one point in the future, instead the amount is received every single year for X years. Like the classic example would be a lottery, where the prize, once it reaches a certain level, typically the lottery doesn't pay out all the money at once. They might, for example, take $100 million lottery prize and give you $10 million a year for 10 years rather than all at once. That would be an example of an annuity because it's 10 million, the same amount every year per year. And so we run into this a lot in financial securities. We see like bonds, for example, as we'll see, are priced this way. And so it's important to know how to calculate present and future values for annuities as well as lump sums. Now, my plan here was to break up these lessons into nice little manageable bite-sized pieces, I guess you could call it. So what I'm going to aim for is to typically have each recording be, let's say, an hour or so in length, because otherwise it gets to be a bit much, I guess, but you can certainly watch them as often as you want. But I think we'll stop right here. And then tomorrow, we'll pick it up where we left off. And then we'll take it from there. I have to sit down and figure out exactly how many of these would be appropriate for the schedule that we have. I'm not sure. It's probably going to wind up being, let's say, 3 or so. I'll let you know about that. But for now, we'll stop here, and then you can watch this, and you can absorb it, and recover from it, and then there should be roughly 3 every week. I don't think there's any vacations. We do have a Memorial Day, but that shouldn't be a problem. So that's how we'll probably aim for that. Maybe once in a while we'll have more than 3, but that's probably going to be about right. We'll see. So anyway, now, by the way, I do want to mention here too that after we're done, maybe this chapter, maybe the one that comes after it, at some point, and we're going to take a sort of a detour and we're going to quickly review the properties of the VBA language, because you're going to want to write or do your examples with VBA. And so every time we introduce a new topic after this, I'll give you examples in VBA, not just Excel, but in VBA as well. So you can get some practice seeing how the language works. And so we'll see. And for what we're doing here, you really don't need VBA. It's not complicated enough for that. But where it really pays for itself is when there's a lot of repetitive calculations. For example, if I, for some reason, needed to do this for every possible compounded frequency from 1 to 365, well, I could still actually do that the way it's set up here. But for certain applications, it doesn't really make any sense to try to do this directly in Excel. And that's when VBA can pay for itself, where there's a lot of repetitive grinding out of numbers. So we'll get to all that fun stuff very soon. But for today, I think we've covered a lot of excellent, exciting new material. And I'll see you all tomorrow. Okay, bye.